All right, so the last video ended up being a little bit longer than I was anticipating. I had it listed as lecture 1A as far as what I wrote at the beginning, but since that video was so long, I'm just considering that lecture 1. This video, I went ahead and wrote down a lot of the key points, and at the end of the video, I'll do a proof. And this will be considered lecture 2A, and in this lecture, I'll do a proof of the triangle inequality. So previously, the main points from the last video was that we gave an introduction to the course. We briefly went over field axioms. We talked about an ordered field, and using the real numbers as our ordered field, we proved these four things, these four listed bullet points. And recall that if A is greater than B, that's if and only if A minus B is an element of P, where P is a set of positive elements. All right, so these are the four things we left off with. And now I'm going into absolute value. So if F is an ordered field like the real numbers, we define the absolute value function to be a function from, and you can think of it as F cross F into F, but it's so pretty much just understood. They just write it as F to F, make things a little bit easier. But it's the absolute value of X is defined into the two pieces. It's equal to X if it's X is greater than or equal to 0. It's equal to negative X if X is less than 0. And I listed a bunch of I guess, properties with absolute value. And so I will show the proof. I'll go ahead and I do a proof for part G. So in this video, we go over, and I went ahead and worked out the proof, but we're going to go, I'll explain it. So we go over a proof of this. And then at the end, we prove the triangle inequality. Otherwise, they aren't very entertaining proofs. So I'm just going to save you to try A through F. I'll show G and H. So it's just stuff that we already sort of know. Absolute value of A is greater than or equal to 0, and it's with equality if and only if A is equal to 0. And that IFF, that's how I'm going to abbreviate if and only if. The absolute value of A is equal to the absolute value of negative A. Part C, negative absolute value of A is less than or equal to A, less than or equal to the absolute value of A. Part D, the absolute value of a product, A times B, is the same thing as the absolute value of A times the absolute value of B. Part E, 1 divided by the absolute value of A is equal to the absolute value of 1 divided by A, if A is not 0. Part F, absolute value of A divided by B can be broken up as a quotient of absolute value of A over absolute value of B. And again, B can't be 0. And then part G, absolute value of A less than or equal to B, and that double arrow is supposed to mean if and only if negative B is less than or equal to A, less than or equal to B. And that's the one that we're going to actually go over the proof. And then the triangle inequality. So it's the triangle inequality is going to be used a lot throughout this course. It's the absolute value of A plus B is less than or equal to the sum of absolute value of A plus absolute value of B. And then part J is called the reverse triangle inequality. And so we do make use of H and J throughout the course. Actually, really G, H, J. I mean, really all of these, but H is so important, it's got a name. So it's got the triangle inequality name. And So for part G, I guess before I do that, here are some triangle inequality corollaries. So I labeled them as K and L to continue with our properties of absolute value with inequalities. So the absolute value of the difference of x minus y is less than or equal to the sum of the absolute value of x plus absolute value of y. And then L is the absolute value of the sum of x plus y is greater than or equal to the absolute value of the absolute value of x minus the absolute value of y. All right, so these are the various properties we'll use throughout the course, and again, it's kind of dry type of proofs, but I figured in this video I'll go over G and H. All right, so for G, we want to show that absolute value of A is less than or equal to B if and only if negative B is less than or equal to A, less than or equal to B. And so what I have put in yellow is sort of the thought process or the scratch work that goes behind the proof. And what I use in red is the actual proof. So first, let's discuss the thought process for the proof. So we have an if and only if proof. So we're going to do both directions. And I use, this is the forward direction for so that means we're going to start with the assumption of A, absolute value of A less than or equal to B in the forward direction. And then the backwards direction, we'll use negative B less than or equal to A at less than or equal to B. So for the forward directions, we're trying to show, so WTS wish to show negative B less than or equal to A less than or equal to B. So from part 4, what we did in the previous video, or went over in the previous video, by part 4, I meant at the beginning right here. We're going to make use of this. All right, so I just labeled that as number 4, Roman numerals. I could probably have better names for these, but I wrote it over again. So it was, if A is greater than B, C is less than 0, then A times C is less than B times C. So that's what we know from part Roman numeral 4 at the beginning. Well, we have the assumption that absolute value of A is less than or equal to B. So that's basically the same thing as absolute value, or B is greater than or equal to the absolute value of A, right? This is the same thing as just writing it like that. So if we think of B in our place of A, and we think of the absolute value of A in our place of B, and we use -1 as a number C that's less than 0, and if we multiply both sides by -1, that reverses the inequality. So where it has B less than or B greater than or equal to the absolute value of A switches to be negative B less than or equal to negative absolute value of A, based on using Roman numeral 4. All right, and that's using -1 in for C, and I'm just using variable change. So we also know that negative absolute value of A is less than A, which is less than or equal to the absolute value of A. And that's from, where was it? That's from here, from part C. All right, and this will take care of the forward direction as I can string together what we know as far as B being greater than or equal to the absolute value of A, and negative B being less than or equal to the negative absolute value of A. Because we want to show negative b less than or equal to a less than or equal to b. So for the proof, again, we assume absolute value of a less than or equal to b. We're wishing to show that negative b is less than or equal to a, which is less than or equal to b. All right, that's what we're trying to show. All right, so multiplying both sides by -1 gives us negative absolute value of a. So by multiplying both sides to -1, I'm talking about star. So I called it star. We multiply both sides by -1. That gives us double star, where it's negative absolute value of a greater than or equal to negative b. And that is by the justification of using 4, Roman numeral 4. Okay, so that's using that part. And I wrote it in the proof as this is the same thing as negative absolute value of a greater than or equal to negative b. That's how I wrote it in the proof. All right, and that's using Roman numeral 4. So we also know from C and those list of propositions or properties of absolute value that the negative absolute value of a is less than or equal to a, which is less than or equal to the absolute value of a. And so I labeled that triple star. So we're going to combine these 3 key points, quote unquote. So we have the first key point was absolute value of a less than or equal to b. The second key point, that the negative absolute value of a is greater than or equal to the negative b. And the third key point is that negative absolute value of a less than or equal to a, which is less than or equal to the absolute value of a. And we can string together the following inequality. So we have negative b less than or equal to the negative absolute value of a, and that's from double star. And then we have negative absolute value of a less than or equal to a less than or equal to the absolute value of a. So that's from triple star. And then we have absolute value of a less than or equal to b, and that's our assumption. So that's our first star. So in other words, we have negative b less than or equal to a, which is less than or equal to b. All right, so that completes the proof for the forward direction. Now the backward direction, we're using the assumption this time that negative b less than or equal to a less than or equal to b. And we're wishing to show what we started with the assumption in the previous one. So we're wishing to show that the absolute value of a is less than or equal to b. And I broke it up so a, the number a, could be greater than 0, less than 0, or equal to 0. And so you could break it up into 2 cases and use the definition of absolute value. And right, absolute value just says absolute value of x is equal to x if x is greater than or equal to 0, and then negative x if x is less than 0. Okay, so using that definition, in the case, I can combine a greater than 0 and a equal to 0 in its own case using the definition of absolute value. So that's why I have case 1, let a be greater than or equal to 0. Then the absolute value of a is equal to a, which we know is less than or equal to B, because that's part of our assumption. The other case would be if A is less than 0. So then that means the absolute value of A is equal to negative A, just by the absolute value definition, which then means negative absolute value of A is equal to A. And we know that negative B is less than or equal to A. So that implies that just changing A with negative absolute value of A, that implies that negative B is less than or equal to negative absolute value of A, which we can multiply both sides by -1 and use our Roman numeral 4 bullet point, and we get that B is greater than or equal to A. All right, and that, in other words, A is less than or equal to B. Okay, so, and that takes care of the proof, right? Because that's going to be the two cases. So for A, it's either greater than or equal to 0, or it can be less than 0, making use of the definition of absolute value. So here's the proof. Again, we start with the assumption that negative B is less than or equal to A, less than or equal to B. We wish to show that the absolute value of A is less than or equal to B. So A is either positive or negative or equal to 0. Using the definition of absolute value, we can combine the cases of A being positive and equal to 0 as its own case. So that's case 1. All right, so for case 1, by the definition of absolute value, since A is greater than or equal to 0, then the absolute value of A is equal to A. So it follows that the absolute value of A, which is equal to A, is less than or equal to B. And that's making use of the assumption that A is less than or equal to B. Hence, we've shown for case 1, when A is greater than or equal to 0, absolute value of A is less than or equal to B. Now the second case, if A is negative, so by definition of absolute value, since A is negative, the absolute value of A is equal to negative A, which means that negative absolute value of A equals A. So we use the assumption. So again, we have two assumptions here. We have this one, negative B less than or equal to A, and then the other assumption is A less than or equal to B. So this time we're using the assumption that negative B is less than or equal to A. All right, using that assumption, and we know that A is the same thing as negative absolute value of A, I can basically do a variable change. So instead of where I have A right here, I have it as negative absolute value of A. So negative B less than or equal to negative absolute value of A, which multiplies both sides by -1 and flips the inequality sign, making use of Roman numeral 4, which gives us B is greater than or equal to the absolute value of A. In other words, absolute value of A is less than or equal to B. So that's, in either case, we've shown for both cases, we've shown absolute value of A is less than or equal to B. All right, so that's the proof for part G of those listed properties or propositions. I think they're the right word. But you know what I mean, those different bullet points. So now the triangle inequality proof. So the triangle inequality says for two elements of the field, the absolute value of the sum of the elements is less than or equal to the sum of the absolute value of each element. So absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y, where f is an ordered field like the real numbers. So we're going to focus our attention on the real numbers. So this is the scratch work. And with the scratch work, I actually start with what we're trying to show. Right? So what we're trying to show, absolute value of x plus x, or absolute value of x plus y is less than or equal to absolute value of x plus absolute value of y. All right, so that's what we're trying to show. And we know from the last proof that the absolute value of a is less than or equal to b if and only if negative b is less than or equal to a, which is less than or equal to b. So using that, we can think of our x plus y as our a, and then the whole quantity, x, absolute value of x plus absolute value of y, put it in parentheses. So that reinforces that's what we're using in spot of b. So this will be like our negative b, and then a, and then b. So that's just using what we knew from the previous proof. All right, so then if I distribute the negative, that gives us negative absolute value of x minus absolute value of y, less than or equal to x plus y, and then I just dropped the parentheses of absolute value of x plus the absolute value of y. And we know for each component, so like because of part C, knowing that negative absolute value of a is less than or equal to a, less than or equal to absolute value of a, we can state that negative absolute value of x less than or equal to x, less than or equal to absolute value of x, and the same thing for y. Now this isn't the proof, because I started with what we're trying to show, and sometimes it helps to go backwards. So for the actual proof, I'm going to start from the bottom and work our way up. All right, and that's actually what I wrote here. The actual proof, I need to start at the bottom. So the proof like I said, you start from the bottom. So because of, we know from part C of those listed properties, or where we have negative absolute value of a less than or equal to a, less than or equal to the absolute value of a. We have that for x and y real numbers. We have basically the negative absolute value of x less than or equal to x, less than or equal to the absolute value of x, and then negative absolute value of y less than or equal to y, less than or equal to absolute value of y. We can sum these two together. So and when we sum those together, what do we have? So we'll have negative absolute value of x minus absolute value of y less than or equal to x plus y less than or equal to the absolute value of x plus the absolute value of y. Okay, then since I could essentially bring the negative so that it's negative absolute value of x plus absolute value of y. And then less than or equal to x plus y. And then just for sake of since I put that in parentheses, I'll put this in parentheses as well. So x plus absolute value of y. Well, because of what we know from part G, so let's see, so all right, so from part G, so we know so that's what we know, absolute value of A less than or equal to B, if and only if negative B less than or equal to A, less than or equal to negative B. So that means I can use that knowledge to translate this as into being the absolute value of x plus y less than or equal to the absolute value of x plus the absolute value of y. This is like my A, and this is like my B. Or that'd be negative B, and this is B. So, all right, and that's what we're trying to show. All right, so again, these are probably sloppy proofs, but I figured it helps to see the thought process, and that's what this is. And this one I started from what we're trying to show and just kind of worked with it a bit to see, well, what do I know from before and how can I apply it? And then I got down to some spots where I was like, okay, if I go backwards, I can end up at what we're trying to show, which is really what this proof is doing. All right, so that's it for this video. The next video, I'll talk about this supremum and infimum. All right, so I'll see you in the next video.